Hi again, and welcome back to the second half of lecture 11. In this one, we will squint really hard until we cannot even see individual galaxies anymore and take a look at the large-scale structure of the universe itself. To get a little overview of this, the universe, as we have seen before, consists of clusters and voids, where the local group is located in a void but rather close to some clusters and superclusters. So you can ask yourself, well, the local group is not empty. It is quite the opposite of empty. We're here. How can it be in a void? Well, the answer is that yes, the density of the local group is larger than nothing, but it is low compared to the density of galaxy clusters. So statistically and in the big picture, the local group still counts as a void. The distribution of galaxies in the universe is clumpy and uneven up to scales of around 250 megaparsecs. Once you get well beyond that scale, it is more or less smooth. We will get back to what that exactly means later on in this lecture, but it is enough to say that once you get above a certain scale, the universe, as we say it, is isotropic and homogeneous. The large-scale properties of the universe, as far as we can see, do not change noticeably once you get to scales of 250 to 500 megaparsecs and above that. The local group and the nearby clusters and superclusters are all part of a megastructure that is called Laniakea, which means the immense, sprawling, widespread heavens in Hawaiian, which is the language it has been named in because it was discovered through years and years of studies from the Keck telescope, which is built on top of the volcano Mauna Kea in Hawaii. So Laniakea is the largest scale at which matter has had the chance to interact gravitationally. This does not mean that this is a gravitationally bound structure. It is not. Laniakea is actually expanding along with the general flow of the universe, whereas the individual clusters it is made up of do not. So that means that the future of Laniakea is that its individual parts will be kind of torn further and further apart, but each individual cluster that it is made up of will not be torn apart. There would just be further between them. So Laniakea is simply the largest scale at which we can see that any two galaxies has ever had a chance to interact with each other, to affect each other with their gravity, meaning that they have some kind of coherence at this point, but that coherence is, as mentioned, not going to last. Laniakea contains around 100,000 individual galaxies distributed over a number of clusters and superclusters. Here we have a map, an overview map of Laniakea. It's always a little bit difficult to show these things, show things that are so thoroughly in 3D in 2D. But I think this is a pretty good attempt at this. And if you look at it, you can see that the local group is situated around here, where we have what's called the Virgo supercluster sitting around here. Then there's the so-called Centaurus supercluster here, Pavo Indus supercluster up here, and a bunch of other superclusters down here. But it is quite clear to see that we have these strings of clusters, right? And where these strings of clusters meet and collide in these knots, we have the large superclusters. I think this is a really cool map. And this is not a simulation. This is an actual map of 100,000 or a couple of 100,000 individual galaxies. But we actually have maps on even larger scales. So here is a map of Laniakea in its context. Here you see a map like before, but with Laniakea being this yellow thing you see here, with the Virgo supercluster here, the Centaurus supercluster here. the Pavu Indus supercluster here and the local group sitting here right in the center. And as you can see, we are again surrounded by other like nodes and strings and so on, clusters and superclusters and large voids in our immediate neighborhood. I don't know if you can even call it a neighborhood anymore on these scales, but in our like super clusterly neighborhood. So as we have seen before, on the largest scales, galaxies are distributed in what we call the cosmic web. You see this map of the cosmic web as it is being mapped out by the Dark Energy Survey, and that galaxies are concentrated in filaments and walls, and especially in superclusters in these nodes where the filaments are meeting each other. And we have these enormous voids of scales of maybe 50 to 100 megaparsecs in between them. And together it is all distributed in a structure that basically is similar to a huge cosmic sponge, basically. This structure is way more clear and way more well-defined and pronounced than the local structure in the local group and the surrounding clusters, which seems way more random. And this is a tendency that we generally will see, right? That when you look at smaller and smaller scales, things seems more and more like random and different from place to place. But once you kind of zoom out and squint really hard and look at the very, very big picture, it becomes way more regular. It becomes way more ordered almost to look at. Let's take a look. Back at the Uchu simulation that I showed before, just to give another idea of the scales here. This box here has a scale of about 10 to the 9 light years. This is a huge, huge simulation. And then we zoom in on that. So this is the zoom in of the small box, and we see that this one has a much larger scale, but this box, this scale bar here is about 100 million light years across, which is give or take the general scale of this box here in the center where we have this supercluster sitting. And when we zoom into it to ever smaller scales, we get into this thing here, which looks like a single galaxy, right? But it's not. This is not a single galaxy. This is a huge galaxy cluster where each one of these small ones here perhaps is a Milky Way sized dark matter halo. And there's just like hundreds, if not thousands of Milky Ways worth of dark matter, worth of galaxy in this relatively small volume that we see here. It's important to point out again that this is a simulation, not a map like this one here was, but it's also very reassuring to see that this, on the largest scales, the simulations and the observations actually agree really well, which is, of course, by design, right? There are many, many simulations that don't really agree very well with the observations. Then we discard these simulations. We rule out the physics, that the physical assumptions that we made in these simulations. That is, after all, why we make simulations in the first place, right? We use them to try and test physics, test physical assumptions. If they agree with our observations, then we iterate further on them. If they don't, we reject them, and we have now ruled out that these assumptions can be true. The way we kind of quantify this homogeneity or inhomogeneity of the universe on various scales is by the so-called two-point correlation function, which is a measure of how unevenly distributed matter is in a given space, including the entire universe. We have this quote by Peebles from 1980. It says that given a random galaxy in a location, the correlation function describes the probability that another galaxy will be found within a given distance. So for a completely random distribution, the chance of finding a galaxy each in two random volumes dv1 and dv2 at the same time, if they're separated by the distance r12, is given as the square of the number density of galaxies times the size of the two test volumes. Right? For a completely random distribution, this function is constant. This function is flat. It only depends on the relative sizes of the two, or on the sizes of the two volumes. However, if galaxy locations are correlated so that they are more or less likely to be found on certain scales than on others, then we get a more general formulation of the function from before, which we can see here, which says that the probability now is given as the same as before, plus this factor here, which is called 1 plus psi as a function of the separation vector, the separation distance between the two test volumes. And this function is called the excess probability to find another galaxy at distance r12. And so basically, if this number is less than 0, then it means we have, if this number is less than 0, it means we have a void or like an underdensity, right? And if it is higher than 0, it means that we have an elevated, like overdensity, an elevated probability of finding galaxies within a given distance. Now, if we have very large and very wide galaxy catalogs, we can actually measure the 2-point correlation function. And what we have found is that the 2-point correlation function is a power law on smaller scales. You can see it here. It is simply r over r0, where r0 is what we call the correlation length, which is around 5 megaparsecs, to this exponent, which is called gamma or minus gamma, where gamma is around, again, completely empirically, is around 1.8. So there's a significant excess on scales less than 5 megaparsecs, as you can see here. That is around where we see this cutoff around here, right? Where it is around 1. This kind of shows us the clustering of galaxies. But if we look at scales larger than that, it starts dropping off faster and is no longer a power law. And once we get up to scales of maybe 60, 70 megaparsec, co-moving megaparsecs, I should say, not just physical megaparsec, but co-moving megaparsecs, we see that the correlation function starts oscillating around 0, meaning that there is a balance basically between the overdensities and the underdensities, which means that for all intents and purposes, at these scales, the universe is essentially homogeneous and doesn't have any, what we could call any structure anymore larger than these scales. That was it for today. The discussion questions that we should think about till we meet is A, discuss why the fraction of cool core clusters is expected to change over cosmic time, that is, also change with redshift when we observe them. And question B, do you think galaxy clusters are fully virialized systems? Discuss what affects the time it takes clusters to reach virial equilibrium and how we could possibly observe whether a cluster is virialized. That was it for today's lecture. Thank you so much for staying with me this far, and I will be looking forward to talking to you all at the lesson itself. Bye for now.